Hello everyone. So let's discuss the last problem of CP contest, that is exponential numbers. The problem statement reads as follows. Exponential number is the sum of different powers of a number n. Find the ideal smallest exponential number for the specific n when these exponential numbers are arranged in ascending order. So let us first try to understand what the problem statement means. So we know that if we have some numbers and we can power them. So like 3 power 0 is 1, 3 power 1 is 3, 3 power 2 is 9. So what exponential number definition is given, we can add those powers. So let's see it for 3. So okay, so let's see what, like we can have 3 power 0, we have equals 1, then we can 3 power 1 is 3, 3 power 2 is 9, and so on, like 27, 81, like so on. So what the question says, that we can add some of these values. So like we can add 1 and 3, 1 and 9, or in different combinations. So let's try out what all values we can get. So first of all, to go systematically, let's take one number at a time. Like we can choose only one number. So what numbers we have? 1, 3, 9, 27, 81, and the list goes on and on. So now we take any two and add them. So the numbers can be 4 if 1 and plus 3, then 10, 1 plus 9, 28, then we can also get 12, 9 plus 3, then 9 plus 27 will be 36, then 27 plus 1, 28. So the same list goes on and on. Then we can take three numbers at a time. So if we take 3, 1, 3, 9, so what we will get? 13. Then 1, 3, 27, we will get 31, and so on. We can take 4, 5, like 4 elements at a time. So we have a collection of different numbers which we obtained by summing up the different powers of 3. Now the question says we have to sort them in increasing order. So if we just sort what numbers from what numbers we have get, so it's like 1, 3, then the next number is 4, and then we have 9, then I see 10, 12, like this, 13, and I have not taken all the numbers, so I may have missed. So what we are doing is we are calculating all powers of the given number. Let's say we calculate n powers. So by basic maths, you may be knowing that what we are doing is, first of all, we are taking one element each at a time. So the number of ways is nc1. Then we are taking two numbers at a time, so nc2, then nc3, and the sum of all these till ncn will be 2 power n minus 1, because we are not considering the case of nc0. That doesn't matter, one case. So 2 power n. So let's consider what our n is. N we can get is maximum 100. So 2 power 100. Imagine it's a very large number of the order 10 power 30, like that or so. So obviously these number of operations we can't do in 1 second, because in 1 second we can at most do 10 power 8 operations. So if we try to do this and print the kth number, what we have to do? After sorting, we have to print the kth number. So in the case of 3, we have to print the fifth number. So you see 1, 2, 3, 4, 5. The fifth number is 10th and the answer is 10th. So if we try to do this, we are generating 2 power n numbers and then sorting takes n log n in any language, C or Python. So we are generating 2 power n numbers, and 2 power, like say we are given n equal 100 in one of the test cases, that will be a very large number and it will take millions of years to run the code. So that's not an efficient approach, but this is what the brute force approach is, the approach that comes first in our mind. So now let's think what can be the efficient algorithm. So see, like something binary representation and all. So if we say like binary representation, in binary representation of 2, what we write is 0 is written as 0, like we take 4 bits as of now, then we write 1 as this, then 2 as this, then 3 is written like this, 4 is this, like this. These are powers of 2 in in base 2 notation. This is very common, like you may have seen it already. Now what is the base notation, base 3 notation or any base n notation? So what you do is, like when you have base 2, the only numbers you can have in this number is 0 or 1. Same way in base 3 notation, you can have only 0, 1 and 2. So your numbers will look like 0 will be like this, then 1 will look like this, then you can have 2 here, so 2 will be like this, but you can't have 3, so 1 will get carried over and you will get this. So this in base 3 notation is 3, while in base 2 notation like in base 2 notation it was 3 only. So like that you can continue. Then this was 0, 1, 2, then 3, then 4 will be this. Okay, so I think I am going right. Let me check once. Okay, sorry, I just said 3 was this in base 3 notation, 3 was this, while in base 3 notation 3 is like this. So you see changes. So and if we want to convert any base n notation, like you can go and write any notation in like this. So let's continue this one as of now. So 0, 1, 2, 3, 4, then 5 will be like this, and 6 will be okay. So you can continue in this method, right? So what we need to do now is we see the powers of 3 will always be in like when we were talking about the powers of 2, so let's not consider 0. 1 is not a power of 2, so yeah, so the 2 power is like this, so it will have only one the 1 in, like only 1 in its representation, in its base notation. Because if you know, when we convert any base notation into a decimal number, what we do is we start from the lowest index and we multiply this index with power of 2 power that particular index we are on. Index here is index number. So this is the way of changing a decimal number, base 2 notation into a decimal number. For any number you do like this. So for this number you will do is 1 into 2 power 0, so it will be 1. Then this number will be 0 into 2 power 0 plus 1 into 2 power 1 plus 0 into 2 power 2, like this. You must be knowing how to convert a binary number into a decimal number. So in this case base 3 also will be converted in the same way. So just the difference, instead just the difference will be this 2 will be replaced by 3 and the same continues. So what will be the powers of 3 look like in base 3 notation? So first will be our the first will be 1, because 3 power 0 is 1. So how we can write is, this is 1 in base 3 notation. Then the next is 3, so 3 will be this. Then next is 9, so 9 will be like this. Then is 27. So you see, we only have a single 1 digit in the whole representation, in the base n notation or the base 3 notation. For this particular case we have just one one digit in the whole binary representation, because if we add any one more, then we will have two terms when we are converting into a decimal number, because the first number will be some power plus the second number in power something, so we will then it will won't be any power of that number. So I hope you get the idea that whenever we have some power, will have only one digit in its representation. So now, how it simplified this work by converting into a this numbers. So see, now you have all the powers. Now take any combination of number and add them. Now you know at the 0th place I am from the right shift from the right place I am calculating the 0, 1, 2, 3 index. So only there is one digit in the whole powers of 3 that has 1 in its 0th index, that is 1. Then in the whole sorry, in the whole list of powers of 3, we have only one digit which has the digit 1 in its base 3 notation at the first index, and so on. So we don't have any number like this 0, 1, 0, 1 like this. We won't have any number. This won't be any power of 3. So in any combination, if you add, what you will have is at any index in the representation, either there will be a 0 or there will be 1, nothing else. You can't have 2 or you can't have 3. 3 obviously you can't have, but for the higher numbers, like if we are considering base 4 notation, then you can only have 1 and not 2 and 3 when you add these types of number. So let's consider like what we did. So if we add and take any two numbers and just add them. So if I take first number and the second number, these are the numbers. So if I take the first and second number and add them, what I will get is 0, 0, 1, 1. Then I take some other combinations. So like I can get 1 and 3. If I add, I will get this. Then 1 and 4 if I add, then I will get this, and many such combinations. Okay, so on. And similarly you can take some 3 numbers and add. So you will see you get only zeros and ones in the representation, because there was one there is only one number in the whole powers, in the whole list of powers of 3, that has 1 in its first place or in the second place or in the third place. So like that. So what we see is that we have generated all these numbers. See, okay, now let's try to sort them in order. So also we have those single digit numbers also, like these also remain in our list because we can choose only one number. So these are like the if we choose only one number, then we choose two numbers, then we can have a list in which we choose 3 numbers like this, and like so on. Okay, let's now arrange them in ascending order like we did previously. So we will get this, then if you know the next number will be this. I am arranging them in ascending order, then this. So this is the ascending order I am doing, so and so on. So I have placed them in the ascending order. So a clear distinction that you will see in here is these are just powers of 2. Now I am not saying any power of n, sorry, not power of 2. These are numbers written in the binary representation or the base 2 notation. Compare this with this. So this is 1, this is 2. If you convert them into decimal number, considering this is base 2, this is 3, this is 4, this is 5, this is 6. And if we take the 5th number here, fifth number is this is 1 2 3 4 5. This is our fifth number, but in actual reality this is base 3 notation. So let's have this number separately here, and if we convert into decimal, so we will have 1 into 3 power 0 plus 1 star 3 power 1, 3 power 2. So this is 9 plus 1 10, and the 10 is the actual number we have to get as an answer. So let's recap what we have done here is, so we get the base, like the notation from here, the n, and we write all the numbers of n in its base n notation. Like base, for this particular case we are seeing the base 3 notation, so we write all the numbers in base 3 notation, write them in ascending order. And what actual fact that we found, or the what actual observation we made is, when we arrange the numbers in ascending order, we get a list that is just similar to numbers, all the natural numbers, when they are written in the binary representation. So we can get the kth number or the ith number from here, and if we convert it back into the original number from the base it was in, we get the required number. So this is one of the algorithm that is much efficient, because just need to calculate the ith number in binary representation and check and not check and just print it's in the original form in the base, convert them from the base n to the decimal representation. So let's try to code it out now. I will just copy it. Okay, so first let's code it in C++, then we will go on to Python. So first of all, we are given two numbers, n and id. So id we can say like let the variable be k. So int n and k. K is denoting the id. Okay. Then let our answer let initialize, and also because these are powers and these can get really big, so in C++ we have to keep a thing in mind that int can only hold up to certain value. So for large values, what data type we use is long int. That's not an issue in Python. So in C++ we will use long int, and let our answer be 0 as of now. And let's initialize a variable long int power and 1. Now what this p will do is, when we are calculating converting back the number into the original decimal representation, so we use, like if we had 0 0 1 0 1 and we this is in base 4 notation, let's assume. So when we are converting into decimal representation, so we will use 1 into 4 power 0, then 1 into 0 into 4 power 1, then 1 into 4 power 2, and so on. So this 4 power 0, 4 power 1, 4 power 2, this thing we are storing in a variable p. So every time we move on, we will just multiply it by the n we get, so that this we don't have to deal with this number repeatedly. Then I am writing this for int I is 0, I is less than 32, I plus plus. Now let's see what is this for loop doing and what is 32 doing here. So in competitive programming, 2 power 32 is a very large, not in competitive programming in general, 2 power 32 is a very large number, and it and it comprises all the numbers that you can think about, that the range can be think about, like 2 power 32 is very large number. So we are iterating over all those 2 power 32 numbers. It helps us to iterate over all those numbers. How it helps, let's see. So if this k and 1 power I, so let's see what this means. So first of all, what does 1 power I means? Sorry, 1 shift operator I means. So this 1 power I is equivalent to 2 power I. So it's just another way of writing this. The double less than operator is known as left shift operator, and it helps us to power a number. You will read more about it when you read about bits, bit masking. So this is just powering 2 power I. So it's just another way of writing 2 power I. And this is AND symbol. If you know what is bitwise AND, so let us have two binary numbers, 0 0 1 1 0, and another number as 0 1 0 1 1. Okay, so bitwise AND, in bitwise AND what we do is we have for every bit, like this is a bit, this is a bit, for every corresponding bit of two numbers, we multiply them. Like, you know what is truth table AND OR, so like that, 0 0 0 0 1 0 1 0 0 1 1 1 0 1 0. So this is bitwise ANDing. So see, k number, when you write it like this here, and when you are doing bitwise AND, it is automatically converted to its binary representation. So k, let k be anything, then k will be converted into its binary representation. Let k be like let k be 5. So the binary representation will be this. Sorry. So k is this, and what we are doing is for every power of 2, like I previously said, when you are powering any number, so powers of 2 will be like this. These are all powers of 2. So you will get 1 only at, you will get a single digit 1 in the whole number. So let's write any of the power, like assume you write this. And when you bitwise AND them, what you interesting thing you will see is 0 1 0 0. So whenever you AND them, you will see that you get a number that is not 0. So that means the particular bit in k was set. Like, this helps us to find which all bits in the binary representation of k are 1. And for every that bit, we get that bit and multiply with these, like I just said, this 4 power 0, 4 power 1, or any n power something. So that it helps us to find the number of ones in the representation. These are known as set bits in bit masking. So this is a way of this is a general way, k and this, of finding the set bits, the number of the bits that are set to 1 in the binary representation of k. This is a very standard way of calculating this. And if the set is this is 1, then we add that to our answer. So we add that answer plus equal p. What we are doing is, like, p we initialize to 1. So let me write it. You will get the essence, p star equal n. So whatever index we are having, like we may be at, like, first we are at 4 power 0. So p is 4 power 0 1 initially, and we add that into our answer. why we are not multiplying that bit? Because we are sure that it will be only 0 or 1. So if it's 0, we don't care. If it's 1 power anything is that number only. So we are adding that number, and like that. In this case, the set bit will be 0. If condition will not be followed, so it will not run. Then in this case we will add, so p will be till then converted to this 4 power 2, and we add that into our answer, and so on. And finally, when we are out of our for loop, we will print the answer. Let me comment it out. Okay. So let's try to run our code. Okay, so it passes, and if we submit this code, okay, so you see all test cases have been passed. Once we write in it Python, then I will just go over the algorithm once again. Let's first write the same in Python. Okay, so first of all we get n and k. And then for I in range of 32, first of all let's initialize our answer 0 and power variable to 1. So if k and bitwise and with power of 2 comma I, so 2 power I power. So this expression is checking if that bit is set, that if it's a particular bit we are iterating over is 1. If it's 1, then we add the particular power, and in every iteration we are multiplying it with n. Finally, when we are out of the loop, we will print our answer. So let's try to run this. Okay, so there is an error. Okay, I have to use map. Okay, input.split also. What error is there now? N and k, I am mapping it to int. Okay, so sorry, I have messed it up. N comma k equals map int input dots. Okay, and that's how map is written. Okay, so it passes the test cases. Let's submit it. Running, I guess. Yeah, so all test cases pass. So what we have done is we get the input and we initialize our answer with 0, and the powers we are dealing with as 1, because every time we will multiply that powers. Then we are iterating over every possible number, and this is a way of iterating, like you are not even going to all the numbers to power 32, but still in just 32 operations you are covering all the numbers. And you check if the kth bit of the particular ith bit of k is 1 or not. If it's 1, you add that number and you are multiplying the p every time, so you get that correct power, and finally you are printing the answer. If you have any doubt in the algorithm, just go back to where I was explaining the algorithm and try to take another number like n equal 4. I was taking for n equal 3, take n equal 4 or n equal 5 and try to solve one example test case on yourself. So that was it. So also let's talk about the time complexity. So the time complexity, you are using a for loop and you are iterating for 32 times, so and there are no more for loops, so the time complexity is just O of 32, or you can just say O of 1. So that's very less time complexity. So that's all for exponential numbers. Thank you.